Hello everyone, I'm Tianshi Xu from Peking University. Now I'd like to present our new work titled Breaking the Layer Barrier, Remodeling Private Transformer Inference with Hybrid CKKS and MPC. This is a joint work with my collaborators Wenjie Lu from TikTok and Jiang Ruiyu, Yi Chen, Chen Qilin, Renshen Wang, and Meng Li from Peking University. Here is an outline. I will first give some background on private transformer inference, then explain the motivation behind our method, followed by our proposed BERT framework, and finally I will share some experimental results. Transformer-based large language models are widely deployed in many data-sensitive scenarios, such as healthcare, finance, and personalized assistance. In these settings, protecting both the model and the user input is critical. Cryptography-based private inference offers strong and provable security guarantees. The server learns nothing about the client's input, and the client learns nothing about the model parameters. We focus on the typical two-party inference setting, illustrated here. The client holds private input data, the server holds a private transformer model, and after one round of private inference, the client only learns the model's output, while the server learns nothing. There are two main cryptographic approaches to achieve such two-party private inference. The first one is fully homomorphic encryption, FHE, in a non-interactive manner. Unfortunately, FHE struggles with complex nonlinear layers, leading either to poor accuracy or extremely high computational overhead due to high-degree polynomial approximation and costly bootstrapping operations. Another solution is combining HE with Secure Multi-party Computation in an interactive manner. This hybrid HE and MPC approach gives high accuracy, but at a huge communication cost. For example, a single BERT-base inference requires around 60 gigabytes of communication in state-of-the-art scheme. To summarize, FHE cannot efficiently or accurately handle nonlinear layers. While hybrid HE and MPC achieves high accuracy, they suffer from massive communication overhead, which is where our work focuses. Our design follows an optimization golden rule. Accuracy comes first, followed by communication, and finally computation. In other words, we minimize communication overhead as long as accuracy is preserved, even if this requires more computation. This prioritization is well justified, since computation can be more easily accelerated and parallelized. Next part, the key motivation of BLB. The common hybrid HE and MPC framework is straightforward. They use HE for linear layers and MPC for nonlinear layers. However, this comes at a cost. Frequent conversions between HE and MPC and truncations lead to over 80% of the total communication, as seen in previous works like BERT and Bumblebee. This becomes a serious bottleneck when deploying large models. So our goal is to reduce the communication overhead in hybrid HE and MPC framework for transformer inference. On this slide, I will explain why frequent conversions and truncations occur. Let's take the example of a linear layer followed by a Jialu nonlinear layer. The client provides encrypted input X, and the server provides the weight W. First, the linear layer is evaluated under HE producing an encrypted output, int y. Since the foreign Jialu is nonlinear layer, it must be evaluated with MPC protocol. But mainstream MPC protocols work on secret shares, so we need an HE to MPC conversion to transform int y into two shares, y0 and y1. Then before entering the Jialu layer, we also need one truncation. This is because both HE and MPC operate in fixed point arithmetic. And multiplication causes the scale to square from s to s squared. Truncation can restore the scale back to s. Both conversion and truncation rely on MPC subprotocols, which require a large amount of communication. So that's why HE and MPC conversions and truncations dominates the cost. Prior work tried to reduce the communication by fusing consecutive linear layers. Here, linear layer fusion refers to using HE to evaluate consecutive linear layers within one single communication round. It can eliminate all conversions and truncations between consecutive linear layers. For example, in this figure, the two consecutive matrix multiplication QK transpose in a self-attention layer can be fused, delaying communication until after the fusion. That is, we evaluate the two matrix multiplication consecutively using HE without interaction. However, linear layer fusion often shows insufficient communication reduction due to the following three limitations. The first limitation is the limited flexibility. This coarse-grained fusion across neighboring layers limits the fusion patterns. For example, only the two consecutive matrix multiplication QK transpose can be fused in one transformer block, resulting in limited communication reduction. The second limitation comes from using BFV for HE. Previous hybrid HE and MPC frameworks adopt BFV HE, but BFV HE works on fixed point arithmetic and cannot reduce the scale. The ciphertext scale grows exponentially with the multiplication depth. This means both the plaintext bit width and the ciphertext bit width explode exponentially, causing inefficiency. The third limitation is that after fusion, you are forced to use ciphertext CT matrix multiplication in HE, which is extremely more complicated than ciphertext plaintext matrix multiplication. The key reason is that adjusting the packing of intermediate ciphertext involves complex HE operations like HE rotations. As a result, the BERT requires approximately 20 times more computationally intensive HE rotations for fused CT method compared to unfused ciphertext plaintext protocol. Next, I will introduce our BLB framework. The key idea of BLB is simple but powerful. In transformers, even nonlinear layers such as Jialu or Leonon are actually composed of multiple linear operators, like multiplication and addition. For example, the Leonon layer includes multiplications and addictions, and Jialu is often implemented with a polynomial approximation, which also involves many linear operators. Therefore, our intuition is that nonlinear layers should no longer be treated as indivisible units. a fine-grained analysis is required. This motivates us to break the traditional layer-wise evaluation to operator-wise evaluation and fusing adjacent linear operators. We first decompose layers into operators, classifying them into linear operators and nonlinear operators. Then, fuse all adjacent linear operators across layers. That is, we evaluate them within a communication round. By this, we can eliminate all conversions and truncations between adjacent linear operators. Let me show you an example in this figure. The last two operators of the layer known layer, the subsequent fully connected layer, and the first three operators in the following Jialu layer are all linear operators that can be fused. By applying BLB, we can eliminate all of the truncations and 55% of HE and MPC conversions. Specifically, BLB includes three components. The first highlight is fine-grained fusion. We systematically analyze the computation graph at the operator level, establish a standard definition of operators, and classify them into linear and nonlinear categories. Finally, we identify the legal fusion patterns for linear operators. The second highlight is secure CKKS to MPC conversion protocol. We adopt CKKS HE instead of BFV to effectively control ciphertext bit width growth. However, we found that previous CKKS and MPC conversion protocols were insecure, leaking intermediate results. To address this, we designed the first secure protocol that supports the conversion between CKKS and MPC. The third highlight is our rotation-efficient Matmor protocol. Fused ciphertext metric multiplications are extremely expensive, so we designed a protocol optimized for the two main operations in multi-head attention, QK transpose and Softmax times V. We also observe that multi-head attention naturally involves benched Matmors, which allows us to pack multiple benches into a single ciphertext and thereby reduce HE rotations. On top of this, we apply the baby step, giant step BSGS optimization to further reduce the rotations. Compared to BERT and PowerFormer, our protocol achieves a 29 times and 8 times reduction in HE rotations, respectively. At last, I will introduce our experimental results. BLB is implemented using the SEAL and EasyPC libraries, with GPU acceleration built on Phantom FHE. Following prior work, we evaluate BLB on GPT-2-base, BERT-base, and BERT-large. We compare BLB with existing private transformer inference frameworks, including hybrid HE and MPC frameworks such as Iron, BERT, and Bumblebee, three-party computation framework Sigma and MPC Former, and the FHE-based framework Nexus. The key results are shown in the table on the right. In short, BLB reduced communication by 21 times compared to BERT and 2 times compared to Bumblebee. In terms of latency, BLB achieves up to 29 times speedup on CPU and up to 13 times speedup on GPU compared to prior work. To summarize, BLB breaks the one-layer, one-protocol paradigm, enables operator-level fusion with CKKS and MPC, achieves significant communication and latency reduction. It's all about this talk. Thanks for your attention.